Sorry.
Oh,
All right.
we're ready. Go ahead.
Okay. All right. So hello. My name is Dong Yoon Lee. I'll be presenting GraPhy, a graph-based, physics-guided urban air quality modeling for monitoring constrained regions. You can see that I'm not on the author list. That's because the first author, Shangjie couldn't make it due to a visa issue. So he owes me steak dinner. Yeah. Okay, I'm doing him a favor. So him along with Kevin Hu and Shijia Pan from the University of California, Merced, we'd like to present this work. Getting started, we see that air quality directly impacts people's health. According to a recent study from the American Lung Association, around 130 million Americans live in areas with unhealthy air pollution levels. This can lead to drastic consequences, health-related, such as 29% of lung cancer deaths created due to air pollution. Not only that, we see a positive correlation between pollution and children asthma. So not only does it affect a lot of people, there's a lot of dire consequences that come along with it. So we find that monitoring this air pollution information to be essential. For example, if individuals had access to this fine-grained air pollution information, they might take a different route to work that's less polluted. Or if they have to live in a more polluted area, they can make more proactive measures, like wearing a mask or other PPE. Also, governments can enact better policies, can make better decisions, such as if they had access to this fine-grained information, they can maybe put a school in a less polluted area, for example, for zoning laws purposes. Also, governments, if they know where the pollution happens, the pollution sources, they can have better control through regulation. So this all sounds like really good ideas, but it's not that simple. Where I live, and Shangjie lives, we live in the center of California, USA, called the San Joaquin Valley. Here we have very unique geographical characteristics. A lot of cows, basically. Other than that, we have two valleys that surround this area. What this does is it traps a lot of air pollution, like a bowl, around this warm air. Also, we use this land in various ways, such as for factories or for farms. So this creates different levels of pollution and has different characteristics as well. This creates a lot of challenges for us. Ironically, the place with the most amount of challenges is also most required for monitoring. Unfortunately, there's other challenges that are just for monitoring as well. Let's take a look at some cities. For example, a city outside this area, like Santa Clara, we see that it's more well off and therefore has a lot of more densely deployed sensors. In a place in this area, like Tulare, we see a more sparse deployment. Also, we see a similar trend in meteorology data. If you look at near San Francisco, you might have 100 plus weather stations, while in places near Madera or Fresno on the right side, you might only have one weather station for the whole city. So this coarse-grained information makes it very hard to do fine-grained monitoring, right? That just makes sense. Because of this, the low spatial resolution for these areas make fine-grained monitoring especially challenging. All right, so let's get how other people tried to solve this. They basically tried to solve how to get the fine-grained information through interpolation. There's a group of these works that use stationary sensors from existing sensor networks to spatially interpolate air quality. These include geostatistics models, which try to use additional geographic information, spatial temporal models, which use both the spatial information and also time series data of these sensors, historical time series data, and also graph-based methods. However, because most of these methods are purely data-driven, they require a lot of training information, a large training data set. For sparse deployments, like in my area, the Central California area, getting a lot of information is very difficult. There's a low data availability. Now, how about for other works that uses mobile sensing? So for like mobile sensing, putting sensors on drones or cars and then moving the sensor around to different locations, right? You might be able to better your accuracy for this interpolation strategy. However, it requires additional infrastructure. Actually, when I go to school every day, you actually have to go, you can't go through a road. It's all gravel path. And it gets worse in other cities too. Sometimes the infrastructure is not there for public transportation, for roads, or even if you're using drones for communications, there might not be any beacons or signal there. So we try to position our solution to use the existing static sensing networks, but try to adapt it for a more sparse interpolation strategy. Shangjie asked himself this question, and I will ask it too. How can we accurately model fine-grained air quality with constrained monitoring resources? We decided to build upon the latest work based on graph neural networks because intuitively we can model this sensor network like a graph, right? Very intuitive, right? Also, neural network, everyone uses it, so why not? We can represent the nodes as the sensors, and there are geographical relationships as edges. By modeling a GNN based on this structure, we can allow the node and edge features to be learned through passing the input sensor data throughout the graph and aggregating it to predict a new location. Let's take a deeper dive into this. So to better understand this process, we can look at an example of a more data-driven GNN, the examples we saw before. So using air quality sensor locations to generate a graph shape and the sensor readings and wind information as input features for the nodes and edges, we can train by iterating through each sensor location as an unmonitored location and comparing the predicted air quality with the actual reading. During inference, we generate a new node at an unmonitored location and uses the existing trained GNN model to predict this new location data. So we see that the node in red, right, is the new node. We initialize it, and we use the same wind information, and then we try to predict it. This is our interpolation method. This data-driven process enables end-to-end learning, but is less accurate for sparsely deployed locations because of the low data availability. So we modified this architecture to include a physics-informed module that allows the model to more efficiently learn the graph relationships. So we introduced GraPhy, a physics-guided graph neural network design. This equation might look very intimidating, but you're all smart. You should know this, right? So if not, I'll give you a rundown. You might have seen this before. It's the convection diffusion equation, right? It's usually used to model like fluid dynamics and such, right? But it's also used historically for data-driven models for air quality monitoring. I'll explain the parts to simplify things. So first of all, we have a diffusion section that describes the movement of pollution due to the different concentrations of air of pollution. And then we have convection that describes the movement of pollution due to external forces like wind. And then finally, we have the local part, which describes pollution sources. So like factories and farms might have part of this coarse-grained local part of this convection diffusion equation. We use 3 separate subgraph modules to learn each of these phenomena separately, and then fuse them together with a graph fusion layer to describe the change of pollution over time. As an analogy, we can think of a diffusion if you know how you put milk and coffee together, right? Like without stirring, the milk slowly seeping into the coffee, that would be a diffusion process. You stirring would be a convection process, and pouring the milk in would be a local process. So if you use that analogy, it becomes really intuitive to separate all these 3 phenomena. And we call this whole process one GraPhy layer. We use the wind data to model the convection module. For the other modules, like the diffusion module and the local module, you can read about it in our paper. But for time purposes, I will only be covering the convection module. As shown before, in the San Joaquin Valley, where I live, we only have city-level wind data available. This poses challenges, as all the nodes will have the same wind feature. As a result, we decided to model the convection on the edges instead of the nodes. Consider this. Let's say we have an edge connecting I to J on the left-hand side, where the input is the node, and the edge features and the output is the updated node feature. So we have the node feature, edge feature. As the node features are initiated at the sensor readings, the edge features are the steady wind information. So that includes the velocity, the angle of the wind relative to the angle relative to the sensor direction, and also the distance relative to the sensors. By using this, we could update all the node features, which would be initiated as the original air quality data, to create new features that could propagate and aggregate throughout the graph. By using this convection module with the other diffusion module and local modules, GraPhy is able to adapt to these sparse deployed environments. So how do we combine this with the GNN model we already have? We take the original plan of the GNN, where we generate this graph structure, but then we add multiple GraPhy layers in front of it as these node features to generate a new interpolated PM 2.5 reading. Interesting. So when we modify the structure of the data-driven GNN, the solution hopes to predict better air quality predictions through this sparsely deployed environment when we do this inference process. To evaluate the solution, we chose a city in the San Joaquin Valley, Fresno. I actually lived here before. There's also a lot of cows near the college here, where we have 41 PM 2.5 sensors, one citywide wind sensor, so that's really important, and the time range of all of winter, basically. And then we have a temporal resolution, a sampling rate of 1 sample per hour, so an hourly sampling rate. And then we have a train validate test split. If we look at our results, we see that compared to the other baselines, especially looking at the graph neural network baselines, the IG, NNK, and GEO, we see that the mean absolute error is least among all of them, even compared to the graph neural network structure, showing that indeed the additional physics-informed structure helps to better generalize with a low data availability. Also looking at the coefficient of between the correlation of the actual predicted values and the actual values and the predicted values, we see that GraPhy performs best here too. Moving on to an ablation of all the different modules for this GraPhy layer, the diffusion, convection, and local, we see that each of them contribute and synergistically help produce a better accurate reading due to the physics-informed subgraph structure. So we see here that actually convection, those without the convection module, so you see the second one on the left-hand side, D plus L, performs worse than those with the convection layer. So C plus L, D plus L, and all three. And of course that the one with all three performed the best. Looking at the evaluation for different model sizes, we actually find a very interesting point for this one. So the smallest model size, only with 3 GraPhy layers, actually performs very similarly to the largest model size, which is really cool because that means our model can be actually computed on mobile or on edge. So all in all, basically, our system, not only can it accurately interpolate spatially different air quality information, but also it can do it on the phone or edge or anywhere that you can compute anything. So we have a lot of interesting future directions we would like to discuss, which include a dynamic version of the GNN structure. If a sensor fails or we want to add new sensors to the existing network, how can we dynamically change our GNN structure? And also maybe introduce multiple different types of data sensor networks that maybe can learn different parts of air pollution or air quality, a form of crowdsourcing this different information, maybe taking a picture or through drone information, getting more data that way, and also finally for government policy purposes, maybe characterizing some of these pollution sources. All in all, we conclude that GraPhy does indeed accurately predict the interpolated PM 2.5 information, the air quality information against other baselines because of this physics-informed method. And also, we showed in our evaluation that through this physics-informed method, even with a low data availability in these sparsely deployed environments, we're able to accurately determine the air quality in these unmonitored locations. Thank you.
Thank you for the interesting talk. Just a couple questions. First of all, do you try to optimize the location of the sensor so that you can see different result accuracy?
All right. I can use the excuse that I am not the first author, so I have no idea, but I will answer the question anyway, okay? To the best of my ability. So the thing is, we want to utilize the existing sensor network that are already available. So we have no say in like how we can move the sensors optimally to the optimal location. It's just wherever people want to place sensors through crowdsourcing or individuals who want to buy their own sensor but connect it to the public network, right? We get that public information that way. The interpolation strategy, what it's supposed to do is even if the placement is not truly optimal for air quality monitoring, right? Hopefully the interpolation strategy can make up for that through basically this physics-informed method, right? Let's say if you put your air quality sensor in a box, for example, or like somewhere that's not optimal, let's say like a very high up altitude or low altitude, right? Hopefully we can make up for that with our physics-informed method. Does that make sense?
Well, partially, but still scientifically still interested to know, given a landscape, where is the location to place the sensor if I could, so that I can maximize my prediction accuracy, right? So this is still a valid scientific question. I understand your viewpoint from actual implementation. Sometimes you don't have a choice, but it doesn't prevent the researcher from asking what would be the optimized location to place, right?
Sure.
So maybe a related question is that just for the set of sensor you have, did you try different number of like the graph neural network with the size, like the node, you can range from 1, 2, 3, 4, and look at the accuracy, whether or not you can see some phase change, like the phenomenon that once the number of sensors exceeds certain threshold, suddenly your accuracy become pretty good. Well, below that threshold, the accuracy may not be very good, right? So.
Sure. So I believe from the limited information I do have, we actually did we kind of investigated what the saturation rate should be for the optimal sensor to accuracy ratio, so that you don't waste additional sensors, even if it's because it's already too accurate, right? You don't need more sensors in that area, right? I think for the general question of how many sensors are what's the optimal density of sensors to accurately interpolate air quality data, and also for sensor placement, right? Both of these questions, I think, we actually do try to investigate in a separately, right? For this study, the reason why we try to use existing information, right, is because sometimes we don't have control over placement due to crowdsourcing efforts for people, right? We can't really control how they do it. I guess we can inform them, right? Maybe that can be a future work, right? We'll look into maybe how to optimally do placement and also what the optimal density is for sensors to accurately interpolate stuff.
Okay,
I
thank
think
you.
there's definitely longer conversation could be had over lunch.
Sure.
But thanks the speaker again.